Ever pondered over why metals are not crystals? Well, you're about to unravel this mystery. Metals, when in a state above their melting point, behave as liquids. Their atoms are randomly arranged and relatively free to move, much like guests at a party, mingling without a strict seating arrangement. But here's where things get interesting. When these metals are cooled below their melting point, they undergo a dramatic transformation. Just as partygoers might take their assigned seats when the main event begins, the atoms in metals rearrange themselves, settling into an ordered, crystalline structure. You might wonder why this sudden shift from chaos to order. It's all about finding stability, or more precisely, a low-energy state. Picture this. You've had a long day, and you come home to find your room in a mess. You could leave it as it is, but that would be a precarious balance. Instead, you tidy up because an organized room provides a sense of calm and stability. In much the same way, metals transition from a chaotic high-energy state to a stable low-energy state. And their most stable state is a repeating pattern of atoms, not a random jumble. This pattern, or crystalline structure, isn't just a neat arrangement of atoms. It's the lowest energy state for metals. And it's a state they can settle into quickly when solidifying from a molten state. So in essence, metals transform into an ordered crystalline structure when cooled, seeking stability and lower energy, much like the fractal energy of lightning. This is just the tip of the iceberg when it comes to the fascinating world of metals and their crystalline structures. We'll delve deeper into the universality and variety of these structures and explore the intriguing Widmanstätten patterns observed in meteorites. So stay tuned for more captivating insights. Don't forget to subscribe and make sure you don't miss any new content, and join us on our journey to gather knowledge one video at a time. Are all metals crystalline, you may ask? Let's delve into that. It's fascinating to learn that nearly all metallic elements, with the exceptions of cesium, gallium and mercury, exist as crystalline solids at room temperature. This is due to a strong tendency in metals and alloys to crystallize regardless of their method of formation. This being a part of their nature, a natural characteristic, if you will. You see, whether they are created by thermal processing or through other techniques such as solution reduction or electroplating, metals and alloys exhibit this crystalline tendency. This is because their atoms can rapidly settle into organized stacks when solidifying from a molten state. In fact, their lowest energy state is in a stable repeating pattern rather than precariously balanced in a random jumble of atoms. This is what sets metals apart from crystals, while both are considered crystalline structures. But what's even more intriguing is that metallic elements can exist in different forms. They can be of a single crystal, they can be polycrystalline, where the material is composed of multiple crystals or grains, or they can be amorphous, much like glass. The structure of a metal can greatly affect its physical properties, including strength, ductility, hardness, electrical and thermal conductivity, and corrosion resistance. Moreover, the crystalline structure of a metal can influence its behavior under stress. For instance, single crystal metals with their uniform structure can exhibit unique mechanical properties. Polycrystalline metals, on the other hand, with their multiple grain boundaries, can be more resistant to cracking and deformation. So, while it's tempting to lump all metals together due to their shared crystalline nature, it's crucial to remember that there are significant variations among them. Each metal with its unique crystalline structure brings something different to the table, resulting in a diverse range of applications and uses. Thus, the crystalline nature is a rather universal characteristic of metals. But, as we've seen, within this universality exists a world of variety and complexity. Let us explore this diversity further as we delve into the variety in metal crystals. Did you know that not all metal crystals are the same? Let's delve into the fascinating world of metallic crystals. You see, metallic elements can take on a variety of forms. They can be single crystals presenting a continuous and unbroken lattice that extends throughout the entirety of the structure. Picture a never-ending staircase, each step a neatly arranged atom, each flight an ordered layer. But metals can also be polycrystalline. This term describes a material made up of many tiny crystals or grains. Consider a beach, where each grain of sand represents a crystal. Each grain is ordered internally, but the overall structure is a patchwork of these individual grains, each oriented in a different direction. Then we have amorphous metals, which are quite intriguing. Unlike their crystalline counterparts, these metals lack a long-range order. They're more like glass than a typical metal, with atoms arranged in a disordered, non-repeating pattern. Imagine a crowd at a rock concert, all jumbled together with no discernible pattern. That's the world of amorphous metals for you. One captivating example that demonstrates the variety in metal crystals is the Widmanstätten pattern found in nickel-iron meteorites. This pattern is a complex interwoven network of two different nickel-iron alloys, kamacite and taenite. Now, the existence of two stable, distinct crystal structures in metals is quite typical. But what makes these Widmanstätten patterns unusual is their size and the fact that they exist in nickel-iron binaries. Similar alloys produced on Earth do not form these patterns. These intricate patterns require extremely slow cooling to form, a process only possible in the vastness of space, where convection or conduction are absent. So, the world of metal crystals is a diverse one, with each type having its own unique properties and applications. The beauty of metal crystals comes not only from their ordered structures, but also from the remarkable variety they exhibit. And just like the metals themselves, this beauty is more than skin deep. It's etched into the very atoms that make up these structures. These are not your everyday patterns, but rather an extraordinary display of nature's artistry found in the cosmos. These patterns emerge from the interlocking bands of two different nickel-iron or Ni-Fe alloys, kamacite and taenite. Kamacite, which is composed of approximately 92% iron and 8% nickel, weaves together with taenite, a blend of about 40% nickel and 60% iron. Together they create the mesmerizing Widmanstätten patterns. But what sets these patterns apart? Why don't we see them in similar alloys produced here on Earth? The answer lies in the cooling process. These patterns require an incredibly slow cooling period, a condition that is only possible in the vast, cold expanse of space. You see, in the absence of convection or conduction, the temperature of these meteorites drops at a snail's pace as they journey through the cosmos. This gradual cooling allows the atoms of kamacite and taenite to align perfectly, creating the distinctive Widmanstätten patterns. On Earth, we simply can't replicate these conditions, just to find out this reason artificially for cost reasons. On Earth, the cooling process is much faster, and our Ni-Fe alloys cool too quickly to form these patterns. Even though human-made alloys with entirely different elements can exhibit a similar morphology, they lack the unique beauty of the Widmanstätten patterns. So, the Widmanstätten patterns are not just a unique feature of certain meteorites, they're a testament to the wondrous diversity and complexity of metal crystals. These patterns showcase the intricate dance of atoms, a dance choreographed by the laws of nature and performed in the grand stage of the cosmos. They remind us that even in the seemingly cold, lifeless expanse of space, there are phenomena of unspeakable beauty waiting to be discovered. So, the Widmanstätten patterns stand as a testament to the wondrous diversity and complexity of metal crystals. They are a reminder that there is always more to learn, more to discover, and more to marvel at in our incredible universe. So why are metals not crystals? We've unraveled this mystery together today. Let's take a moment to reflect on what we've learned. Metals, while not classified as crystals, adopt a crystalline structure at temperatures below their melting point. This is due to their atoms settling into organized stacks when solidifying from a molten state. The lowest energy state for metals is a stable, repeating pattern, not a precarious jumble of randomly placed atoms. We've also discovered that almost all metallic elements, excluding cesium, gallium, and mercury, are crystalline solids at room temperature. Metals and alloys, akin to ionic solids, have a strong tendency to crystallize, whether achieved by thermal processing or other techniques such as solution reduction or electroplating. These metallic elements can exist as a single crystal, be polycrystalline or take an amorphous form, much like glass. And let's not forget the fascinating Widmanstätten patterns, those long interwoven nickel-iron crystals found only in certain meteorites. The structures are interlocking bands of two different nickel-iron alloys, kamacite and taenite. The existence of two stable, distinct crystal structures in metals is common, but what sets Widmanstätten patterns apart is their large size and occurrence in iron-nickel binaries. Similar alloys produced on Earth do not form these patterns, suggesting these patterns require extremely slow cooling, only possible in the vacuum of space. It's been a fascinating journey, unraveling the intricate world of metals and their crystalline structures. We've delved into why metals form these structures, their universality and diversity, and the unique characteristics of Widmanstätten patterns. It's a testament to the wonder of nature and the endless surprises it holds. Always remember, knowledge is power. Don't forget to like, share, and subscribe for more enlightening content. Until next time, keep wondering, keep learning, and hope to see you again. Let this knowledge help you on your journey.